Recording in progress.
Okay, so hi everyone, and welcome to this lecture. So I will ask you to mute yourself, and if you have a question, of course, you can unmute and ask your question. All right, so we are now going forward. So okay, so we are in the process of proving the theorem of existence of Cauchy-Peano-Arzelà. And so the last time we proved this theorem. So if we have a sequence of continuously piecewise differentiable functions which are continuous, so which satisfy those 2 points, I had corrected that, but so there's no t here. Okay, so if we have that, and if so, basically the sequence is uniformly bounded by a constant independently of p and t, and you can put this difference as small as you want, so there's no p. As I said here, there's no p. There's no t, sorry. Then if the sequence is converging uniformly, then U is a solution of the ODE. All right. Okay, so now the key point of today is to actually construct such a sequence. All right. So that's what we are doing today. It's constructing. We are dealing with the construction of such a sequence. All right. So that's, again, that's the whole point of today, is to construct such a sequence which will be converging towards our solution. Right? So let's move on with that. Is there any question? No. Okay, so first of all, let's say today we are splitting the course into 2 parts. First, we are stating and proving the Ascoli Theorem in a form which is suitable for our purpose, right? And then we will finish the proof of the existence of a solution for our initial value problem. So the Ascoli Theorem writes like that. So assume we have a sequence of functions that are Lipschitz with a coefficient k, and they are applications from a compact metric space E with a distance d into a compact metric space F with a distance g prime. Then we can extract from this sequence a subsequence which converges uniformly. In this case, and in this case, furthermore, the limit is itself K-Lipschitz application. So we are going to prove this theorem together. So in the applications, with respect to our purpose, which is to prove the existence of a solution for our initial value problem, here, so in this theorem, ED is a general metric space, but in our setting, E will be, in fact, just the interval 0 t, right? Endowed with the usual distance on R. And this one will be a compact set of R to the M, actually a ball, right? A closed ball in R to the M, all right? Okay, so I propose you to prove this theorem. So I let you 5 minutes to read again the theorem, and then we will prove it by hand, right? So let's go. So we have a sequence here. Of Lipschitz applications, all right? And so what we want to do is extract from there a subsequence which converges uniformly. So to construct this subsequence, we will, in fact, construct some subspaces of n, all right? So my S0 is n, and then from there, I extract one set, S1, which is included in S node. Then I extract S2, and so on, so forth. And I impose that the cardinal of each of those sets is infinite, all right? So this is true for n equals 0, right? Because n has an infinite number of elements. Now, if we assume that Sn minus 1 is already constructed, how I'm going to construct Sn, right? So this is actually the main part of the proof. So first, in order to construct Sn, first since E and F are compact sets, I can cover them with a finite number of balls of radius 1 divided by n. All right. So I can say that E is included in a finite number, or can put 0 or n or 1. So let's put 1. Some for a number capital N. Let's call it Ti. So the n here, the lowercase n, is related with my set Sn minus 1. All right. So I can do that because E is a compact set. So I can cover it with a finite number of balls. And I can do the same with F. Of course, the number of balls is not necessarily the same. And here, let's call the points yi. So I just used the fact that E and F are compact sets. Okay, now I'm going to define a function phi, so phi is from my set Sn minus 1. So, and Sn minus 1 is included in, is a subset of n. So, which means that this is numbers, okay? This is natural numbers. And from each number in this set, it associates some numbers in R to the n, but more precisely, it associates n values. So capital N. Sorry. So yeah. And so yeah, but it's not what I want to do. So because these are, it's not Z, but it's the Y, because it's the Y that I used there. And as I said, and to the n, right? So the y's, I defined it just the slide before. You remember? The y's are defined here. So the y's are those points in R to the m with which I can recover the compact set F, right? Okay. And
excuse
then,
me, teacher.
yes.
We said that Sn minus 1 has an infinite cardinal number.
Yes.
So the y elements, y1, yn prime, will be infinite too.
No. So it's an important point. It's a key point of the proof, and I'm coming to that. All right. It's finite,
okay.
but this is a key point to understand. So thanks for asking this question. This is a good question. So no, it doesn't have to be infinite, but this will imply something which is important. All right. So let's do that. And so here I have a number p, a natural number, and I will associate to that. So some z's, I call it z1, zn, where the z's are z1 is either y1, y2, or yn prime, etc. Okay, and so of course this is not clear because I until now I didn't tell you what are those z's. So those z's are defined as follows, where z1, and so here, sorry, this is like that, where z1 zn is such that so here I have a p, but don't forget that I am working with a sequence up. So here for p I have a up, and so where up t1, so up t1 belongs to what? So each up of t1, it belongs to what? So sorry, I said r to the m, but this is the application. In fact, I'm working with the general f, all right? So here, up of t1 belongs to f, but f is covered by a finite number of balls, which means that up of t1 belongs to one of those balls. And the same for t2, and the same for up of t2, and the same for up of tn. So this will belong to the ball. So the ball's in F, the ball of center Z1, 1 divided by n times just for, you can forget this, you can focus on Z1. So let up of T1 belongs to F, and F is covered by those finite number of balls. And so up of T1 belongs to one of those balls. So the Z1 is one of the Y's. So Z1 might be, I don't know, but is one of those. All right. So now you should understand that my function is well defined. My function phi is well defined, and the space where it lives, it's finite. All right, because z1 is takes its value in the finite set y1, y2, etc., etc. So where z1 it belongs to y1, yn prime, and the same for all, the same for z2, etc., etc. So that's the point. Now, my function phi starts from a set which has an infinite cardinal, but it takes values on a finite set. What is the implication of that? So So is that possible or not?
Yes, it's possible.
But so what's the point? This is possible, but how is that possible?
I think that the function phi eliminates a lot of natural numbers that are not.
So how the function phi can do that?
I don't know, but with the definition of phi.
So the point is what? The point is necessarily, since the space from which we depart is infinite, and the space where which we arrive is finite, necessarily some. So there are an infinite number in the space of departure which have the same image. That's the only way, because it's okay.
Yes, yes.
All right. So it follows that there is one of the points in the arrival space, so I call it again Z1 Zn.
So phi will be constant.
Sorry?
I'm sorry.
Yes.
So phi will be constant over a set, an infinite set.
Yes, you can say that. Yeah, but yeah, you can say that. So, but it's constant, but it's a general compact set. So, yeah, but yeah, it's so yeah, but that's that you can say that. All right, so it follows that there is one of these points. So again, I'm writing it again. such that necessarily, so phi minus 1 of has an infinite number of elements. So and that's the key point. That's the key point of the proof. All right, so the basic idea is related to the question of Mr. Abadi, is that the space of departure is infinite and the arrival space is finite. So necessarily, one of the points in the space of arrival as his so phi minus 1 of this point has an infinite number of elements. That's the only way we can achieve that. All right, now I can define my Sn, because my Sn are defined by induction. So I know S node, which is the entire n, the natural numbers. And when I know Sn minus 1, I can construct Sn by setting Sn equals precisely this set, which is infinite, sorry. So let's write it better. So now we set Sn equals phi minus 1 of this particular point in the arrival space. And so by construction, all right, now I can construct my subsequence. So I could just use the diagonal extraction process, but yeah, that's what I'm going to do. But let's formulate it in a slightly different way. So I'm constructing my lowercase phi here. So phi I use it to construct my subsequence of up. Now I want to construct my u phi of p. So phi is a function from n to n, and it's defined like that. I want to, so I set phi of 0 equals 0. And once I know the first, I construct it again by induction, and in the following way, I just want that if I know phi of n minus 1, I want that phi of n, I want it to belong to Sn. And I just want it to be greater than so another way is to say that I could do phi of n is the element number n of Sn. And that's why this is the diagonal extraction. I couldn't do that, but okay, I use that. All right, it's the same. It's not the same, but the result is the same. So the point is what? So now why I'm doing that? So just forget this definition for a little bit, and now if assume that P and Q belong to Sn. What can you say about the distance? So UP of T and UQ of T. So those are both elements for a fixed T of F. So
they are less than K, the distance of G.
okay, so that's a good point, but you have to
We're
do
going
it.
to use,
Yes.
we're going to use the Lopez-Yan hypothesis.
Yeah, but you see, that's not the same function. So yeah, you have to bring it to the same function. So that's a good idea, but so let's think a little bit more about it. So he wants to use the fact that all the functions of the sequence are Lipschitz with the same coefficient. That's a good idea, but P and Q are different. So you cannot do that directly. So how can we do? How can we do that? No, there are. This is one of the things that we know, but we know other things. So first, we know that the space E, where the T belongs. So the T, I use T because I have in mind my application, but here in this proof, T belongs to a general compact space, E. And E is recurved by a finite number of balls with centers Ti. I have written that in a few slides ago. So I cannot choose directly the fact that my UP is Lipschitz, but I can introduce here a Ti with the triangular inequality. So I'm doing that.
PG.
And here I put P
TI.
Ti. So Ti is one of these, but I choose the I such that T and Ti are at a distance less than 1 over n, because Ti covers my E.
Yes.
Okay. And then, okay, I just want to complete the inequality, the triangular inequality. So if
Plus.
I put, yes.
Right. UPGI. UQ.
Yes.
G.
Yes, thank you. And then I close the loop, if I can say that. Okay, now I can use the fact that UP and UQ are Lipschitz with the same constant. Where? where I can use that here.
For the first distance and the last one, the third one.
Yeah, that's right. So for these ones, I got 2k.
The distance TGI.
Yes. Which is less than 1 over n, but let's do it after. And what can I do with the last term? This one.
It's in the ball. So it's less than 1.
Yeah. So
1 as your n.
it will be 2. It will be 2 because if you have one ball, so you will choose one of the z. So those belongs to one of the balls z. I can call zj. But okay, if they are there and there, again with the inequality, triangular inequality, I got a 2. I get a 2. Yeah, so it's 2 divided by n. Because again, I can use the triangular inequality. So I can introduce the right z, which is the center of the ball, where they belong, right? And they why they belong to the same ball? Because so that's important. So why can I say that they are in the same ball?
Because P and Q are in Sn.
Yes, that's right. And all the elements of Sn belong to the same, have the same image with phi, with capital Phi, meaning that they are in the same ball, or all elements of Sn
Yes.
of the same their so yeah, you got me. Okay, you got it. So that's right. Okay, you can think, if you didn't get it, you have to think a little bit about it, but this is right. Okay, and this, so now I can say that let's add some here. So again, the distance between t and ti is less than 1 over n. So finally I get that this is less than 2 divided by n times 1 plus k. We're almost done. We're almost done. When we are at this stage, we're almost done. We're almost done. Why? Because you see here, now instead of P and Q, I can consider now, if I consider now my subsequence. So I already have defined my subsequence. So U phi P for P belonging to N. So if I took two different P and Q, by construction, if Q is greater than P, they belong to the same space as SP. All right. By construction, I recall you the construction of my phi. So my phi of P belongs to SP. So if Q is greater than P, again, by construction, phi of Q is greater than phi of P, and also phi of Q belongs to SP. So I will get this inequality. I will get that. So if I consider this subsequence, then when I look at the distance between U phi P and U phi Q, for Q greater than P, by construction, this belongs to SP. This belongs to SP. Therefore, I have this so it's a P, right? It's a P. Belong to. Okay, now I'm done. Why? So I will go directly to the point, assuming that you know some theoretical facts. Now, this is a Cauchy sequence. Now, U phi P is a Cauchy sequence in the space of continuous function from E into F with the infinite distance, the sup distance, and this space is complete. So, and the infinite distance is the distance of the uniform convergence. So, since it's complete, every Cauchy sequence converges, and so there exists U. So U is continuous. Such that U phi P converges to U uniformly. Okay, is that okay?
I didn't understand why we introduced the phi. Why we are using the phi P
So that's the
instead
point.
of P and Q.
So no, the whole point of that is what we want to extract a subsequence. Okay, the theorem we want to prove is that there exists a subsequence of the initial sequence. And so that's why I use the phi. The lowercase phi is my subsequence. So U phi P is a subsequence.
Yeah, but I can't see where is the problem with P and Q? Because
no, because you have to extract. So now you have to extract one of these. It's not the whole sequence which converges. It's not the whole sequence, right? Because you left a lot of indexes in your path. So at each, when you construct the spaces S, P, you keep some and you reject others. So, but at the end, I want a unique sequence. So it's not all the U's. I have to choose some. So my phi is just to say which one of the U I choose. That's why the phi is here.
Okay. Can you, sir, can you show me the previous slide,
Sure.
please?
Sure.
So we said that U of phi p is a Cauchy because it's verified the inequality
Yeah, and note that.
above.
So I could add some steps more, and without using the fact that the space of continuous function with the subnorm or the subdistance is complete. It's just two steps. But the key point here is that my inequality does not depend on t. So it is a Cauchy sequence. We say that it's a uniform Cauchy sequence. You can say that. So the inequality here, the right hand side of the inequality, doesn't depend on t. So if you want to make it more palpable, you add a t in the left hand side, and you think about r to the m. And so you have just the norm, and you see that the right hand side does not depend of t. But for each fixed t, you have a Cauchy sequence in r to the m, which is complete. Then it converges for each t. But then, since the distance doesn't converge, doesn't depend on t, you can go to the limit and show that the convergence to this function that you define for each t is uniform.
Okay, teacher.
So the Ascoli theorem, it's a Havre theorem, and yeah, but the idea is this one.
It's not easy at all.
Yeah, it's not easy. It's not easy. You have to go through it again. I have some notes, but I will post the notes at the end of the 3 series of lectures, 4, 5, 6. And I've written the proof there, and I add. So this is a known fact from topology stuff, but in the notes I put the details, so I didn't use that. But yeah, Ascoli's theorem, it's a Havre theorem. Okay, so we proved the theorem. It remains to prove that the limit is itself Lipschitz with the same coefficient.
We have to prove it.
Yes, we have to prove it. We almost did it, but let's consider that it's another exercise. So now, so u is a continuous function defined on my space E. So we want to prove that it's Lipschitz. Meaning that and so I would like to prove that. I want to prove that. Stewart, yes. So I will give it to you. I think you're tired, so yeah. So now, so let's do it.
We will use the uniform convergence.
Yes.
Okay,
Again,
okay.
so yes, you can do that. Yeah, that's what we are going to do. So we can approximate by one of the elements of the subsequence, and using the fact that all the functions of the sequence are Lipschitz with a coefficient k. So yes, so we will use again the triangular inequality. So to be rigorous, I use my subsequence, right? Plus, sorry. And here I put the phi p of s, and then I close the loop. And here I can work with this term and forget the others. So here I put those two terms. And this one, I have that this is less than and then taking the limit gives the result. Because this is going to 0. Okay, so now at the end you have this one is less than this one. So you got it. All right, so let's do a little break. And yeah, so we can do a 15 minutes break. And we'll come back after the break. Meanwhile, you can think about questions. And if you have some questions, we can try to answer them. So this is it for Ascoli's theorem. So do you have some questions? So if not, let's move forward. All right, so I've already spoken about the Euler's method. So basically, the Euler's method is the basic method for approximating the solutions of our initial value problem. However, here we will use it in a slightly different way. So here is the usual Euler method, right? So you split your time interval 0t into n segments, and then u0 is known, is your initial condition, and then by induction you approximate ui plus 1 by this formula. So you have a vector. So here we just put the elements of our vector we put it together with a linear function. All right. So we will define for each time space. So given a function f and an initial condition, we construct a continuous function piecewise linear by this formula, right? So between two so at each time interval here, so for each time interval here, my function provided by the Euler method here is a linear function, right? And its derivative is given by the function f. All right. So hopefully this is clear. If not, just tell me. So maybe you can see where we are going. The functions provided by the Euler method will be our sequence of functions from which we can extract a subsequence that converges to the solution. So that's why I'm talking about the Euler method here. Okay, next. Next, we have to do this remark. So I've defined the open set O at the beginning. So yeah, so let's consider that we have some interval 0 t0 and a closed ball U node R node on which the function f is well defined and it's continuous. Then if I choose a t sufficiently small, we can prove that ut remains in the ball here. Even if u is my exact solution or any solution provided by the Euler method. All right. So we are going to prove it. This is not so hard. You just have to write the integral. So let's do it. Let's do this as an exercise. So we want to prove that I can choose a time capital T, such that my solution will start with the exact solution, and then we will do the same for the approximations given by the Euler method, remain in this ball. Okay, so let's do it. Let's do it together.
So teacher,
Yes.
the solution U is defined on the interval 0 to 0.
So my function f, so let me share here the whiteboard.
I'm asking for the domain of UT, the solution.
Yes, so this we have to so the f, so sorry, it's not, the f is defined on 0 to 0, is defined on O, but you can include these elements in O. Right now, you assume that you have a solution which is defined. And you have to prove that if it's well defined, if it's well defined on an interval 0t, then the solution remains, u of t remains in this ball. That's what we want to prove. So for the exact solution first. So assume that we can define the solution u, the exact solution, on an interval 0t. So this belongs to R to the M. So I want to prove that if t is sufficiently small, then u remains in this ball here. So I just write it like that. U of t is, by definition, u node plus the integral between 0 and t of f s u of s ds.
Yes.
And so I can take here the norm. So for example, the Euclidean norm, and I will get that. But now, since f is defined on the compact set here, as long as
less than,
yeah, is less than a constant, as long as u remains there, right? But since it's there and it's continuous, it will remain there for a certain amount of time. Okay, so this is less than mt, where m is you take the sup, which is the max of f right. So this is true if t is small enough, because at the beginning u of t is u node, and since u is continuous, it cannot escape before a certain amount of time. So now you see that if t is less than r node divided by m, ut remains in the ball. All right, if I choose t less than r node divided by m, the norm between ut and u node will be less than r node. So let's write it like that. If t is less than, I will take the minimum between t0 because I want that t is less than t node and r node divided by m. Then for all t, then I have that t and u of t belongs to, of course, 0t, which is included in 0t node, times so yeah. So this ensures that the solution will be defined. If I have a solution, it will be defined for a given amount of time, meaning that it will not exit the definition domain of f before a certain amount of time that I can compute explicitly. All right, I have an estimate of the time during which the solution is defined, at least. Okay, and the point is, I can also do it for the approximated solutions provided by the Euler method. Now, so now you assume that you, so I don't write the h, but it's the u is provided by the Euler method. So it's not the exact solution here. U is not the exact solution, but an approximate solution. And I claim that I can do the same estimate. So first of all, U is, in this case, piecewise C1. So I can write that also. Sorry. That's wrong. What I was writing was wrong. But what I wanted to write is this. This is true. Because U is piecewise C1. So it's continuous, and I can write that. Now, so can I do the same? I would like to write that. I want to do the same computation, but I cannot do it directly because here U prime of S is not equal to, I cannot write that. So I cannot write that this is equal to Fs US ds. This is false, because now U of S is not the exact solution, is an approximated solution provided by the Euler method. So I cannot write that, but instead, I can write that I know explicitly the u prime, so it's a sum. Because this derivative is constant, because it's in fact this function is piecewise linear, so the derivative is constant, and I can write it. So assuming that I don't know, for example, t belongs to the interval ti plus 1, I can write it as, so the sum of the integrals and the sum of the integrals will be f of now tk and u of tk times h. So since it's the same, I can put it here, plus t minus ti f of ti uti. So assuming that t belongs to the interval ti plus 1, and where I recall that ti equals eh. So I just used the fact that the u prime, actually u prime is a constant on each interval ti or tk plus 1. Okay, but tk plus 1 minus tk, it's h. So I obtain this last line. And so now I can do the same computation. Now I get that u of t minus u node is less than h times this sum. But actually, I will get here. Yeah, so here. Yeah, so here I want E belongs to that. Yeah, so it's I minus 1 here. So hi, but hi is ti. So I get ti plus here. And of course, I have to put the m ti plus, here it's t minus ti. So I get the same. It's mt. All right, so the same estimate applies for a function which is provided by the Euler method. So I have a uniform bound for all the functions constructed by the Euler method. Okay, so so this is not hard. You have to write it if you didn't get it, but this is not hard. So finally, I have the same. I have that u, if t is less than u, where u is an approximate solution, then t uf of t belongs to and in particular you have that so the functions constructed thanks to the Euler method are uniformly bounded on the interval 0t. All right. So that being said, that being said, I started today's lecture with the theorem 7 that we proved last week. And there was two assumptions for theorem 7. The first one is or was that my sequence of UP needed to be uniformly bounded. So this is true with functions provided by the Euler method. Next, we want to prove that the functions constructed by the Euler's method satisfy also assumption 2, which is an estimate between u prime and f of t ut, where u is not the exact solution because in this case it is 0, but an approximate solution. So let's do that. Are you following me or I've lost everyone?
Yes.
It's okay? Okay, so let's do that.
Can you just give us the approximate
Yeah, I will write.
function of Euler?
Yeah, sure. Sure. So let's do so. So what we want to prove is that for a given epsilon, so I give an epsilon here. I want to prove that if h is sufficiently small, then the UH, I drop the h to avoid too much subscripts, will satisfy that u prime of t minus f t u of t is less than epsilon. And so, yeah, so the u is given by this formula ut equals u of ti plus f ti u ti t minus ti. So for t belonging to ti. So I let you think about that. Like I let you let's say 10 minutes to think about that and try to prove that.
We have to prove the first one first.
No, the first, yeah, the first one, actually, we already proved in the previous lemma. This is the uniform bound, but we already proved it. So it's done.
Okay.
So what we have to prove is that.
I think that u prime of t is approximated by u of t minus u of t I sub t minus t of I. It's that's solve the problem. No,
Can you repeat your question, please?
I think u prime of t can be approximated by this quotient by u of t minus u of ti sub t minus ti.
You can speak in French if you want. Go ahead.
Ok. I prime de t est rapproché par le quotient i de t moins i de ti sur t moins ti qui va résoudre, qui va donner cette égalité.
No, so here this line was to answer the question of Mr. Abadi. It's the definition of, it's the way we construct the Euler function. So what we want to prove is that if so ti plus 1 minus ti, by definition of the Euler method, it's h. We want to prove that this, if this h is sufficient, I can, if I choose h, if h is sufficiently small, then I can have that for all t. Okay, so epsilon is arbitrary. I choose it as small as I want, but once it's fixed, I claim that I can choose a h such that this inequality is satisfied for every t in 0 capital T, where my u is not the exact solution, but it's defined. So this is the definition. It was so Mr. Abati asked for me to recall the definition of the function provided by the Euler method. So that's the point. We need to prove it. There's some work to do.
Ici, en fait, on a u du t qui égale à UTI, bon, d'après la définition, plus FTI, UTI,
Yes.
fois t moins ti. Donc, si on dérive u' du t, donc on va utiliser notre hypothèse. Donc, on aura l'inégalité de la première, c'est équivalent en fait à dire la norme de FTI. Bon,
so let's do it slowly. You have a good idea. You said something interesting. So you said that, so if t belongs to ti plus 1, then the derivative of u, I recall, I should write a h, but I don't want, so u is not the exact solution, it's the approximate solution given by this equation. So effectively, if I take the derivative here, what do I get? What's the derivative?
de
Égal à
TI, de
TI,
T.
UTI, en fait, puisque
No.
tout dépendra
No,
de-
this is a constant. This is 0.
C'est seulement f de TI, I de TI.
Yes. Yes. All right, now, so I can plug that here. And try to prove that if h is sufficiently small, then this norm here is less than epsilon. So I can succeed in putting this quantity as small as I want. That's the point. So now, as you said, so as you said, now this is only f ti u ti minus f t u of t. We want to estimate that. For t is not everywhere. T belongs to ti. Yes.
On a que f est lipschitzienne, n'est-ce pas?
F est continu.
No. Yes. F is only
Et
continuous.
c'est un compact.
F is continuous on the compact. Yes.
Mhm.
So, what can I do? So that's right. F
Puisqu'il
is
est continu sur un compact, donc il est uniformément continu sur ce
that.
compact.
Yeah. Yes. 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 Yes.
Et
Yes.
donc, ça va donner une majoration qui ne dépend pas de I. C'est-à-dire une majoration qui dépend uniquement de la longueur de l'intervalle, H.
Yeah, but we have to do the details because here.
C'est inférieur égal à epsilon, non?
Oh, you have different things. You have two variables. So we have to do the details. So we have to use the fact that, so let's forget this for the moment. So as you said, F is continuous on the compact. So it's uniformly continuous there. And I know that the U remains there. I have proven just before. So now I was given an epsilon. So there exists given mu such that if the norm here So T minus Ti plus UTI minus UT is less than mu, then the result is true.
Exactly. The norm of FT by
So
TI
minus F
smaller than epsilon.
Okay, but I want an estimate with only H.
Exactly, but we have the first part of this. La valeur absolue de témoin TI est inférieure à H.
Yes.
Et l'autre norme doit la majorer en fonction de ce qu'on a déjà montré. Oui.
Yeah. So yeah. So now, so this this is smaller than H. And then, so U of T is UTI plus F TI UTI T minus TI. So yeah, if I put UTI on the left-hand side, I take the norm, I get that this quantity, or put it here, it's less than M times H. Because I know that the norm of F is less than M from my previous computations and assumptions.
Exactly.
Okay,
Il suffit
then
de prendre mi tel que prendre H tel que qu'il vérifie que ça est inférieur à mi, ça résout le problème.
exactly. So I want that H plus MH. If I choose H such that, let's do that. So if I choose H such that H times 1 plus M is less than mu, or H is less than mu divided by 1 plus M, I got the result. And the mu depends only on F and my domain of definition of F. It doesn't depend on P or, Okay, so the lemma is proved. The lemma is proven. It's proven. Okay, I claim that we're done for today because so first, do you have any questions?
Sorry, teacher, but I didn't understand the last demonstration.
Here? Okay, yeah.
Yeah. How the definition of the continuity can lead us to.
So Mr. Delbou, explain that for us.
Because when we have that F is continuous in the compact, if we have this property of F, it implies that F is uniformly continuous on the same set by the theorem of Hahn.
Mm-hmm.
Yes. Then by uniform compacity, uniformly continuity, we have that the last inequality is satisfied. If we have the norm of U of Ti minus T U of T, the norm on the norm defined on the compact set, intervalle 0T0 fois la boule fermée. Voilà, c'est la norme définie sur cet espace, c'est cet ensemble compact, est définie par cette forme-là. La valeur absolue de T moins TI plus la norme de I de TI moins I de T. Si le couple T de T, voilà, TI, I de TI satisfait que sa norme est inférieure à mi, ça donne automatiquement que la norme de F2, premier couple moins F2, deuxième couple, est inférieure à epsilon. C'est ça l'uniforme continuité. Et que mi ne dépend pas de epsilon. C'est une constante à prendre uniformément. Voilà, c'est ça, c'est ça la force de l'uniforme continuité. Ça satisfait. Donc, il suffit de prendre H pour qu'il satisfait que cette norme-là doit être inférieure à mi. Puisque cette première partie est inférieure à H, la deuxième partie est inférieure à MH. Alors, la somme est inférieure à M plus 1 fois H. Il faut prendre H tel que M plus 1 fois H inférieur à mi. Et le résultat aboutit directement.
That's right. Is that clear for you, Mr. Abadi? I can go it again for you.
Kind of, but I don't understand what is the relation between this definition.
What is that?
And
what is
our
the what?
results.
What is the
relation between the results that we need to prove and the definition of this continuity? Because we want to prove that U prime minus FGI UGI is less than epsilon. Is
so
that right?
U prime of t minus f of t u of t.
Yes, that's
Yes.
it.
Now U prime, since by construction of U from the Euler method, my U prime is a constant.
It's a constant. Okay, yes.
And this is this constant. This is the derivative of U prime. And so that's U prime. So that's what we want to prove.
Okay. Yes. Now I understand.
So,
yes.
yeah, and sorry, it's U prime of t here. Okay.
Yes, pour ne pas confondre, on peut la définir I étoile. On n'a pas la confondre avec I. On a défini I.
Yeah, it's UH. UH. We can call it UH, but I don't want to write it. Okay, you have to go through it again. Because now we're done. We're done, because if now I came back.
Now it's clear now, teacher. Yeah.
Okay.
Understand that.
Great. So we have the theorem. It's here. This is the theorem that closed the chapter, not the chapter, but the section 2. Now we're done. I'm just telling that to you orally. So we construct a sequence with the Euler method, which satisfies the assumptions of theorem 7, 1 and 2. I can come back. Here are the assumptions.
So the sequence of Euler methods converge the the solution, the exact solution?
I don't know that yet. I don't know that yet. But I can, by choosing my h with respect to the epsilon p, I can construct such a sequence UP that satisfies 1 and 2, thanks to the Euler method. This is okay. I've just proved it. Now, after, with this sequence, during the proof of just now, during this proof, that we have proven that the sequence of functions provided by the Euler method is Lipschitz with a constant m. We have just proved it. If I construct UP thanks to the Euler method, then UP is Lipschitz with the constant m, which depends only on f. So what can I do? I can apply the Ascoli's theorem. And then I can extract from my Euler, from the sequence given by the Euler method, a subsequence that converges uniformly towards a function. And now I can go back to theorem 7, and the limit is a solution of the problem. So that's it.
Yes.
That's it. So I'll let you as an exercise. We have done all the job now here. And this is the theorem. This is the Cauchy-Peano-Arzela theorem. So this whole chapter is inspired by the book of de Mailly, but with some differences. But yeah, this is based on that. So basically, we are done for today. I don't want to charge you too much. Now, we have to settle the projects. So, some of you have chosen their project. So this is the last day today to register for the project. So some of you have already chosen one. So do you want to change? Or are you okay?
No, for me.
Okay. So, okay, so those who are not registered for the project as of today cannot do it after, okay? And so today I closed the list of registered students for the project.